Avery here, and myself along with Anna and Jalen will be representing group RAD, and we will be covering discrete Bayes theorem today. So as a starter, I'm going to go ahead and write down the formula for discrete Bayes theorem just so we're all in the same place, which again, that's the probability of a sub I given B, where B is just some event and a sub I is one of the partitions of the outcome space, which again just is you have an entire outcome space divided into A1, A2, all the way up to A sub I, different partitions that are independent of each other. And so once again, we have probability of A sub I given B, and that equals the probability of A sub I intersecting of B, so the probability that both of these two events occur, all divided by the total probability of event B occurring. And so one of the easiest ways to really grasp this idea and this formula and to see it played out is through an example. So the example with which we'll be working today follows a student who's at recess. So this student, he comes out and he's looking to play with a ball. He has 3 bins to pick from, all of which are equally probable for him to choose from. In the first bin, you'll find 3 kickballs, 2 soccer balls, 5 basketballs. The next bin that is an option is 2 kickballs, 4 soccer balls, 4 basketballs, and that last bin being 4 kickballs, 1 soccer ball, 5 basketballs. So what the student does is he starts by going to whichever bin he goes, and he rummages through, and the first ball he picks up is a soccer ball. Unfortunately, he didn't want to play with the soccer ball, so he throws it back in and then draws a basketball, which he didn't want a basketball either. He's really gunning for that kickball, so he puts that basketball back in. And something that's really important to remember is that all of these events are happening with replacement. And so that's really important because it, once again, just emphasizes that we're not changing this distribution of the balls. It will always be 3, 2, 5, 2, 4, 4, 4, 1, 5 for each of the bins respectively. So the first question we have here today in part A is asking, what is the probability of bin 1, bin 2, and bin 3 being that selected bin that the student is pulling from, given that his first 2 draws were as expected or as earlier, which again is that the first is a soccer ball and the second is a basketball. So the first probability we're going to compute is the probability of bin 1, which I'm going to be writing as bin 1, given that a soccer ball S is the first draw and a basketball B is the second. So the first thing we're going to do is in the numerator, again looking back to that initial formula of having the intersection of the two, so the probability of the bin 1 and a soccer ball and a basketball. So that's going to be 1/3. That 1/3 coming from that each of those bins has equal opportunity to being drawn. So there are 3 bins, so it has a 1 in 3 chance of being picked. And then there are 2 soccer balls, so 2 out of the 10 times 5 out of 10 for the basketballs. And then for the denominator, we're going to have that again. In addition, we'll be adding the probability of bin 2 and bin 3 given, or their intersection with those events happening. So there were 4 basketballs and 4 soccer balls in bin 2, and then there's 1 soccer ball and 5 basketballs in bin 3. And so the first thing we can do is we can knock out those 1/3 again, just because all the bins have the same probability. So then simplifying this down, we get 10 over 100 divided by 31 over 100, which gets us 10 over 31 to be our solution. Next, we'll be approaching the probability of bin 2 given S of B in a very similar approach. The only difference is now instead of bin 1 in the numerator, we'll be having bin 2. So again, that 1/3 probability of it being bin 2 times 4/10 for the basketballs, and then another 4/10 for the soccer balls. The denominator will actually be the same, again, because we will be having the same distribution. 4/10, and then bin 3. Again, can knock out those 1/3 and simplify, which that gets us 16 over 10, same denominator, so 31 over 10, which leads us to 16 over 31, being the probability of the student running up to bin 2 and drawing from there, given that a soccer ball and basketball were chosen first. And the last probability is the probability of bin 3, given that a soccer ball and a basketball were drawn. And something we can actually use here is the complement rule, which will save us a lot of time and a lot of hand cramps. So what we'll do here is we know that the probability of B1, B2, B3, given that a soccer ball and basketball were drawn, have to equal 1. So we'll take 1 minus the probability of it being bin 1, and then minus the probability of it being bin 2, which will lead us to getting 5 over 31 for the answer of it being bin 3. And so with that, I'll pass it off to Anna, who will take us into part B.
We are now ready to tackle part B of our problem. Part B tells us to determine the probability that the next draw is a kickball given the previous 2 draws. So if you recall at the beginning of our problem, we have our second grader out at recess. He selects one of the bins at random, and then from there, he selects a ball out of the bin. It's a soccer ball. He decides he doesn't want it, so he puts it back. He then selects a basketball out of that bin, and he decides he doesn't want it, so he puts it back. So we have 2 draws with replacement from the same bin. Now to solve part B, we can use the information in results from part A. So from part A, the new distribution is and again, we found this new distribution because we had some observations. So again, we had those observations of that soccer ball and that basketball. So I'm just going to kind of denote that as S, B here. So from part A, we had that new distribution. So bin 1 now has a probability of 10 over 31. Bin number 2 now has a probability of 16 over 31. And bin number 3 has a probability of 5 over 31. Now we can use our new distribution and the information given at the beginning of our problem of bin 1, bin 2, and bin 3 to help us determine the probability we draw a kickball on our next draw, given we had that soccer ball and our basketball in our first 2 draws. Now the way we do that is we take our new probability of bin 1, which is 10 over 31, times the probability we draw a kickball from bin 1. So we have 3 kickballs in bin 1 here, so that will be 3 over 10. We then add the probability we have bin 2, that's 16 over 31, and we multiply that times the probability of drawing a kickball from bin 2. So we have 2 kickballs in bin 2. So that would be 2 over 10. And then we add the probability that we have bin 3, so that's 5 over 31, times the probability that we have, or where we will draw kickballs from bin 3. And that would be 4 kickballs in bin 3. So that is times 4 over 10. Now if you put this all in your calculator, you get the fraction of 41 over 155, or if you want to see this as a decimal, this is approximately 0.2645. So for part B, we used the information from part A about our new distribution, along with the information about how many kickballs were in each bin, to determine the probability of drawing a kickball on our next draw, given the observation of a soccer ball and a basketball on our first two draws. And from there, we were able to determine that the probability is 41 over 155, or about 0.2645.
Hello everyone, Jalen here. I'll be covering the final part of the lesson, which involves utilizing the probability distribution that we've just created in order to find the expected value and variance of kickballs drawn. The expected value of kickballs will be written as the expected value E of N given S and B, where N is the number of kickballs drawn next from a chosen bin, and S and B represent the soccer balls and basketballs. Now this expected value is going to equate to 1 times the probability of choosing a kickball, which we found in the previous part to be 41 over 155, plus 0 times the probability of choosing another type of ball from the bin, which will then simplify to 1 minus 41 over 155. So as you can see here, the 0 is going to cancel out the second term, which just leaves us with 1 times 41 over 155 for an expected value of 41 over 155. Now moving on to the variance calculation. In order to do this, we first need to find the expected value of n squared. However, lucky for us, the coefficients on these probabilities are just 0 and 1. So therefore, the equation is just going to come out to the expected value of n squared given s and b is equal to 0 squared times the probability of choosing a different type of ball from the bin, 1 minus 41 over 155 like last time, plus 1 squared times the probability of choosing a kickball, 41 over 155, which again simplifies to 41 over 155. So as a result, the variance of n, or the variance of n given s and b, is going to be equal to the expected value of n squared, 41 over 155, times the expected value of n, that value squared, which is just 41 over 155 squared, and that difference is going to come out to about 0.1945. Now it's important to note that both the expected value and variance would change significantly, along with the entire probability distribution that we've created, if we were to draw the balls from the bins without replacement. So just something to keep in mind for the future. Thank you for your attention, and we hope that we were able to improve your understanding of the discrete side of the Bayes theorem.